Hello everyone and welcome to lecture 11 part 1, threshold problems. So in this lecture we will look at what are threshold problems and actually what is the difference between a threshold problem and a pinch problem and how the threshold problems change the design of a heat exchanger network. Okay. So in the previous lectures, we have seen chemical processes that require both hot and cold utilities. However, this is not always the case. So let's look at this example here. So we have a hot composite curve and we have a cold composite curve, and they are plotted on temperature enthalpy diagram. And if you see there is no overlap between these two streams, it means that there is no heat recovery. So all the heat requirement of this cold stream is actually supplied by this hot utility, that is steam, and all the heat that is available in the hot process stream is actually disposed to the cooling utility, that is cooling water. So not a very efficient process in terms of energy efficiency and heat recovery. So let's look at improving the efficiency of this process by implementing heat recovery. So we select a minimum approach temperature, that is, for example, here 20 degree delta T min is 20 degrees centigrade, and we manipulate our composite curves until we have our closest approach temperature between the hot composite curve and the cold composite curve, that is 20 degrees centigrade. We now have heat recovery in the system, and the part of the hot stream, that is cold stream, that is not actually in part of this heat recovery system get its heat from the steam, and for the hot stream, the part that is not in the heat recovery actually disposed of its heat to the cooling water. Okay, so in this process we already got some heat recovery by manipulating the process streams, but if we want to increase our heat recovery, then we have to move our process stream further by reducing the delta T min. So now we have taken our delta T min to 14 degrees centigrade, and we notice something rather unusual compared to what we have seen before in the previous diagram. So again, we have our shifted composite curves so that we now get our minimum temperature close to 14 degrees centigrade here. Okay. And we see that our heat recovery between cold and hot process has already increased. But what is more interesting is to see that we don't have any hot utility requirement anymore. Okay, so we still have this part of the process stream that needs its heat to be disposed of to a cooling utility, but actually we don't have any requirement for the hot utility. So by reducing our delta T min to 40 degrees centigrade, we have achieved two things. One, that we have reduced our hot utility to zero, and second, that we have increased our heat recovery in the process compared to when the delta T min was 20 degrees centigrade. So what happens if we try and recover more heat by going down to a lower delta T min? Okay, so here we have taken our delta T min approach temperature to 10 degrees centigrade, and we have our heat recovery as previously seen. However, our heat recovery is the same as you can see here, but now we are in a situation where we have actually we have this part of the cooling utility, but now we also have part here as well, and the sum of these two cooling utilities are the same as when was the case when we had 14 degrees centigrade approach temperature. Okay, so the cooling requirement of the process remains the same. We have defined a special type of problem called a threshold problem. And a threshold problem exhibit a threshold delta T min that we have seen in the last slide as being 14 degrees centigrade for maximum energy recovery. Okay, so once we go below that threshold delta T min, there is no further energy recovery and there is no further requirement for additional cold utility or decrease in cold utility. So in pinch problems, as we have seen earlier, we have delta T min equal to 0, like is shown here. We still have a hot utility requirement and a cold utility requirement. So pinch problems are very different from the threshold problems. Even when we have a delta T min of 0 degrees centigrade for pinch problem, there is still requirement for both hot and cold utility that is quietly different from the threshold problems as we've seen in the previous slides. So let's have a look at slightly different format for pinch and threshold problems. So here we are showing our pinch problems initially, and when there is an increase in, for example, the delta T min value, and we are also looking at the effect of that increase in delta T min value in terms of the utilities of the process. So starting at delta T min value 0, we see a requirement both for hot and cold utility. Okay, as we increase our delta T min, we see an increase in hot and cold utility requirements up to whatever delta T min we are looking at. Okay, so this is the case for pinch problem. Now let's compare our this pinch problem to our threshold problem. So for the case of threshold problem, as we increase our delta T min, we have a constant. So we have no hot utility requirement at delta T min 0. But as we increase our delta T min, we see that our cold utility requirements remains the same up to a value of delta T min where we have to introduce hot utility as well. And after that value of delta T min, both the hot utility and the cold utility starts to increase. So this value of delta T min is what we call threshold delta T min value of the process. So there is quite a major difference between pinch problems and threshold problems and how we define the minimum delta T min.